Okay, now this one, I sort of skipped last semester because I said I will talk more about this in this semester, which is Isomorphism Theorems. That's chapter 3. Yeah? Okay, now we have so many algebraic structures. Okay, you remember we have, if something like this, if this is of order 12, we know it's not cyclic, but this is isomorphic too. Okay, because this one both are cyclic and they are relatively prime. If they are relatively prime, we can combine. But these are not relatively prime, so you cannot say they are isomorphic to this. And one reason is that you will not find an element of order 12 because the element in the direct product is the lowest common multiple. Okay, and the biggest element order in here is 2, in here is 6. So the lowest common multiple, the biggest number won't be 12 because 2 and 6 becomes 6. Yeah, the lowest common multiple. So there are many groups that we can do isomorphic. Just now we see that D4 can be also written as isomorphic to a subgroup of S4. We can also prove they are not equal. One is like rotation, reflection, right? One is like a mapping, 1-to-1 and onto. But we can show isomorphism, 1-to-1 onto is a operation. Okay. In this chapter, we're trying to prove the fundamental theorem of homomorphism. Okay. Then we look at these 3 isomorphism theorems, and there's also correspondence theorem. Okay. Then we see how we can deal with factor group. Okay. All right. Fundamental homomorphism theorem. So we have, whenever you read a theorem, okay, you have to understand what's given, and then all the conditions, they are normally given because they are needed. Normally you won't give just for extra. Okay, so we have a mapping, okay, phi from G to G prime is a group homomorphism. When you see this means G and G prime are groups. When you see this, then you know that this mapping is a homomorphism. Okay? With kernel H. Then you have to look back. What does kernel means, right? Kernel kernel is all elements G in G that is mapped to the identity in G prime, right? That is the kernel. All element in G which is mapped to the identity of this. Right, that is the kernel. Okay. Then phi of G. What is phi of G? If you have a mapping from G to G prime, phi of G is whatever the image, right? If you have G here and G prime here, and you have this mapping, if you have G here, this is mapped to the image, right? And whatever is mapped to this is called the kernel. So you have a kernel, and E has to be inside the kernel. Kernel is something that we map to the identity. Okay. Now you can have the image is the whole G prime, or this is mapped to only a part of G prime. Might be not the whole, right? The image might be not the whole. For example, if you have phi from Z to Z, phi of G is probably, I'm just throwing in example. Okay. What is that? 2G. Okay. From integer to integer, but G, the image is 2G, meaning we don't have the odd numbers as image, right? So the even numbers will be here as part of the image, but you have the odd number, right? Co-domain, right? We call it. All right. Okay. So that's why we have that. Then this is a group. Okay. It's a group because the original G is a group, and you have a homomorphism. So it's a group, and you have this mapping mu. Now, kernel of anything is always normal. Okay? The kernel is always normal in the group. The kernel is a subgroup. It's always normal, so we can take the kernel, we call it H. Okay, you take the group G, you take out the kernel, right? So we have this mapping mu. Then this is a group, and mu given by, okay, now this is a coset. So this is coset, right? And this is an image. So if we take G in G, the element here is coset. and here is the image. Is a homomorphism. Okay. Now, you see the word homomorphism around, right? We don't see isomorphism yet, because this is just the fundamental theorem of homomorphism. Okay, now if we have gamma k from G to G mod H is an isomorphism. Okay. Given by gamma G equals GH. Okay, then we can combine this tree mapping by taking G from here, which is actually composition of these two mapping. Okay, so I need another whiteboard. I don't want to erase, but I need to draw. Okay, let me try and draw up there. Okay, so this is the, try to find color. Okay, G here. Okay, then we have phi to G prime, but I put like this. Okay. Okay. Then sometimes we call it, what do we call it? What do we call it? Natural homomorphism. Okay, natural homomorphism is by taking the kernel. Okay, for all group G, there's a kernel of a mapping, and then you can take the natural homomorphism by modding out the kernel. You can get G to G mod H. So by that one, yeah. By that one, you have this, right? Why do I use K here? I use H. Okay. And this natural homomorphism is natural isomorphism. So this is the isomorphism. Okay. Then my mu is from here to here. Okay. So now we start with phi from G to G prime. Call this the image. A group homomorphism, kernel is H. Then this is a group. Okay, and mu from this to there is a homomorphism. And if you have this mapping from G to the quotient group, it's an isomorphism. Then we say that this can be written as from that G, right? If there is a G here, so phi of G you get from in here, right? P of G, you get in here, right? Or you can go that way. You apply G, you go here, and then you apply again into mu, then you get back here in P of G. Right? You take out the G, becomes the coset, and then mu of the coset, you get back phi G. So in this case, they match. Okay, I think it's much easier to see in this way. I will give you one example. Okay, later they use this. So I will not go to one by one line of the proof, but it's given there. You are supposed to go through the proof. So first, I define the mu. Okay, that's the natural one. And if you have two same coset, that is in the kernel. So this is to show that mu, you have to show this mu is well defined. Okay, you cannot have two coset goes to the same thing. Okay, so the first part is to show that if you have two different coset, the image has to be equal. Okay, to show it well defined. And then the next one is to show when you take this, okay, you have to show it's equal to the image. Okay, that's quite straightforward actually. The next part is to show it is unique. You have to show that there is only one mu. This, okay? All right. Okay. Okay. Now, very, very close to this. Oh, no wonder I use K. That's no, because in this one, I want to call it K. But this first one, I call it H. Right. The most important one is what I want to call first isomorphism theorem. It's very, very close to this one. Okay. You don't see that much difference. So first isomorphism theorem is derived from the fundamental theorem of homomorphism. Okay. Right. Let me rewrite. First isomorphism. Since it's very close to this one, I will give example to the next one. Okay, again, let phi from G to G. Okay, again, we want this to be homomorphism. And call the kernel to be K. Okay. Then we want to let this gamma K from G, the canonical homomorphism. Sometimes they call it natural homomorphism. Sometimes they call it canonical homomorphism, like just now. Then there is a unique isomorphism, like just now, right? Mu, right? We use it. Mu from G mod K to phi of G. Or just now I use square, right? Okay. Such that same thing. Phi of X is equal to mu. Okay. Okay, so this one is very, very similar. You see from the previous one that we let this instead of then there is one, and we have this unique isomorphism. Okay. Again, you can go through the proof. See if I can find an example. Okay. We use maybe just a billion. Easy. Billion. So the drawing is very, very similar as before. Okay, I need a mapping, right? So okay. Okay, phi is from Z to Z3. Okay. Phi of N is this is like the conjugacy class or the classes of that number. Okay, so what I have is I have this Z that I want to get only the cosets accordingly. Okay, I need kernel, right? I need a kernel. If I make this isomorphic to Z6, oh no. I want this to be the kernel. So take that out. And I want this to be my mapping. So this is new. What I want is that to break up Z into 3 cosets. And let me think. Three, right? Is Z3? Z3 is okay. So I want this Z. Okay. I want any okay. What is this? 3, right? Yep. Yeah, I want this to be the coset. Any subgroup is normal. It's a abelian group, so every subgroup is normal. I want every element in here break up into 3. So this is what I mean. Only 3. Like you have so many here, Z, but you have Z3, only 0, 1, 3. Okay, so divided into 3, everything is Z can be divided into 3. 1 go here, 1 go here, 1 go here. Right? And the one mapped to 0 is all multiple of 3. I want that mapped to 0. The one mapped to 1 is the one with 1 plus 1. So this is like 1 plus 3, right? 1, 4, 10. That is mapped to 1. The other one, 2 plus 3 is 2, 5, 11, right? That is mapped to 2. So that is my point. So by doing this, I have this mapping. Okay. And I have this kernel because all of this will be mapped to 0, right? This is the kernel. Okay. And by the first isomorphism theorem that exists, a unique isomorphism. So you can actually map this mu by the coset, right? Which is exactly this, right? From the coset, this is the whole Z, but if you take just the coset, that will be this coset matched to 0, 1, 2. 1, 2, 1. So the isomorphism comes from here. So that's one example, right? Okay. Try to find other example for this one. This one is the easiest example because it's just abelian. The other example, if it is not abelian, then the first isomorphism will really help. You don't have to find this. but this one exists. Okay. Okay, I have what time now? Okay, I'll go one more to the second isomorphism theorem. Okay, this one is actually much shorter. Let H be a subgroup of G, the group G, and N normal in G. Then this product H dot N modulo N, the factor group, is isomorphic to the factor group of H intersect with N. Now, the key is that if this become, using the theorem just now, if you have G to be this, right? G mod N, if G is equal to H mod N, you remember when we do exercise in chapter 8 about normal subgroup? If H is a subgroup and is normal, H dot N is also a subgroup. Okay. All right. Try and go through the proof. Let me just give one example. Okay. Okay. This is it. G is 3 copies of integer. Okay, X, Y, Z. It's like R3, right? But this is Z3. Okay, if you draw, they are integers. Dot, 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 right? They are not continuous. H okay, so if you write out, this is like G1, G2, G3, right? Gi in Z. If you write this out, this will be H1, H2, 0. Okay. And N, I let N to be this. These are all abelian, so it's normal. So this is 0 and 1 and 2. Okay, so in this case, if you multiply H by N, right, then it is G. Okay, because how I write this. And the intersection, what is the intersection? The middle, right? Call it what? What do I call it? Oh, I just do it this way. Okay. The intersection is 0, Z 0. That's the intersection. So let's see this. So Hn mod n, this is G mod n. And this is isomorphic to G mod n. So this like cancel, not cancel, but in factor group, this goes away, this just Z mod 0, which is isomorphic to just Z. Yeah. Remember the last class I show you how to get the factor group. Now this one. H mod that. I just put H mod this. So this cancel, this cancel, this also. So that is how you use the second isomorphism theorem. Okay, let me just go ahead and do the third isomorphism theorem, because it's already here. Okay, it's very similar in the sense we have H and N, but we have H, K is normal. H and K normal, but I want K to be a subgroup of H. Okay, then G mod H, see H is normal, I can do this. It's isomorphic to G mod K mod K mod H. That is why I want K and H to be normal, and I want K or H? Sorry. K to be a subgroup of H. Okay, K normal in G, K I want it to be normal also in H. So I can take this. If you see this, this is like, this is wrong, yeah? But I want to show you something like this, right? But don't write like this. No cancel, yeah? This is a factor group with another factor group. Okay, and this is supposed to be normal. If H and K is normal in G, the factor group is also normal. Okay, go through the proof. Right, let me see. Let me see if I can find an example. Okay, example. Okay, so G is Z, H is 6, K is a subgroup of K is 6. K is smaller. K is 6. H is 3. Right? Six is in 3 because 3 has more elements. Okay. All right. So what is G mod H? I want to see this. G mod H is Z mod 3. So again, just now I already write out, right? So 1 is 3, 3, 0, 3, 6, 9, right? Another one is 1 plus 3, 1, 4, 7, 10, and so on. Another one is 2 plus 3, right? 3 plus 3 is again 3 because it's the same thing. Okay, now I want to see. Let me write here. Small here. Okay. Okay, what is G mod K? Z mod 6. So there are 6 of them, right? Because 0, 6, 12, that is the 6. And then 1, 7, 13, 1, and then 2 until 5, right? So there are 6 of them. Okay. So this is actually isomorphic to Z3. This is actually isomorphic to Z6. And I need H1. This is like okay. So you see, you take the first one is 3. 3. So you get all this. Oh, sorry, you get all this with 0 plus, you get all this, right? The second one, when you take 3 plus, you get the rest, right? 3, 9, and so on. So there is only, sorry. There is only 2. You see, if you read out, the first one you take 0, so you get all this, so you get 0, 6, 12, all that, and then you take 3. 3, you add this, you get 3, 9, 15, so you get all the rest. Okay? Now we want to see this. Okay, so there's 3 there, there's 6 there, there's 2 there, right? 3 is 6 over 2. Okay, 3 is 6 over 2. So you can actually write this. And this is isomorphic 2. That's right. Which is actually Z. Okay. So I will stop here. You have to go through the whole chapter. There are other examples. Okay. And also, we will start next class. There's also exercise that you can match as example. Okay, since you have exercise 2 to hand in, for now, just try and do exercise 3, don't hand in yet, because this is very, very similar if you want to understand this. Maybe I will ask you to hand that in the week after, okay, for exercise 3. Yeah, Hannah? Exercise 3 will be the week after. That is to understand this chapter, right? Okay, I'll stop here.